Okay, so in part 3 of this lecture, we are going to do few examples related to circuit analysis problem. So the solution for these examples have been provided to you in solution lecture 15 here. Okay, so you can refer to this solution while referring to my lecture. Okay, so in these examples, we are given a circuit. Yeah, we are given a circuit which is let me see. Okay, we are given a circuit which is consists of the voltage source of delta t, the impulse. We have 2 Henry of inductor. We have 0.25 farad of capacitor, and there is a resistor of 6 ohm here. The question now is to transform the circuit into S domain and draw the circuit. Okay, and then write the equation of the voltage source in the S domain, Vs in terms of Is, and find the IT when the switch is closed at time t bigger than 0 by assuming that I is 0 negative and V 0 negative is 0. Okay, so in this question, we have been given the assumptions that the VC 0 negative of this capacitor and the IL 0 negative of this inductor are 0. Okay, so because the initial voltage and initial current for initial current and initial voltage for both inductor and capacitor are 0, so it is easier for us to solve for the problem. So the task now is to transform this circuit into the S domain and then write the equation of the Vs in terms of Is. Okay, let's look at the solutions here. So we know that this is the conditions given: initial voltage and initial current, right? So when we do the Laplace transformation, delta t will become 1, 2 Henry will become 2s, and 0.25 will be 4 over s. Yeah, 1 over sc. So 1 over sc we have 4 over s, and 6 ohm will remain as it is. So IT will become Is. So we can need to write the Kirchhoff voltage law for this particular circuit. So using Kirchhoff voltage law, we're going to have 1 equals to 2s plus 4 over s plus 6 multiplied with Is. So we're going to have that the Is will be s over 2s squared plus 6s plus 4. Okay, so Vs basically is the voltage across the resistor of 6 ohm. Okay, so across 6 ohm resistor, we can write that the Vs will be 6 of Is, which will be 6 of these Is that we have obtained previously. So 6s over 2s squared plus 6s plus 4. Okay, so we have number 1, we managed to sketch for the circuit transform. Number 2, we have write the Vs in terms of the Is, which is the voltage across the resistor. And number 3 is to write the Vs in terms of Vt, or which is to inverse the Laplace transform for the Vs. Okay, so we know that Is is equals to the question is number 3 is to find the IT, is to find the IT. So I'm going to use the Is which has been obtained from part 2 just now. So S is S over 2S plus 2 over S plus 2, and we need to write this in terms of A partial fraction. So we have A over 2S plus 2 plus B over S plus 2. So this, what I've done is based on partial fraction that we have learned in lecture 13. Okay, so I don't want to discuss further on this. So you can refer to the solutions on your own. Okay, and up we managed to get A is -1 and B equals to 1. Okay, and this will be the Is, which has been written in the partial fraction, -1 over 2s plus 2 plus 1 over s plus 2. And in terms of the IT, we need to do inverse of Laplace transform. That will be -0.5 exponential -t of ut plus exponential of negative 2t of ut. Okay, so this is solution of IT in time domain, yeah? Okay, so let's have a look at the second examples here. So we are given a circuit consists of VRT, then there is a 10 power of 6 ohm of resistor and 1 microfarad of capacitor, and V naught T is the voltage across the capacitor, and the VRT basically is a rectangular function from 0 to 2 with the amplitude of 1. Question number 1 is to sketch the Laplace transform equivalent circuit of figure 3C. Yeah, I need to sketch Laplace transform for this. Then by using Laplace transform, we need to determine the V naught T. Okay, so that's the questions, yeah? Right. So let's have a look at the solution for that. Okay, so this is the circuit in time domain. So when we do the Laplace transform, yeah, and we assume that initial voltage for the capacitor is 0. That's our assumption because in the question there is no conditions given on the initial voltage. So our assumption is initial voltage for the capacitor is 0. So here we're going to get VRT will transform into VRS. 10 power of 6 ohm will be 10 power of 6 ohm. And this capacitor will be 10 power of 6 divided by S, which is based on 1 over SC transformation. Yeah. Okay. So this is your circuit which has been transformed into the S domain. Okay. Number 2 is by using Laplace transform, determine the voltage response of V naught T. Okay. So we need to first write the VRS. Okay. So knowing that VRT is UT minus 2, okay, in which we know that from this problem, your VRT is like this. So we can write the VRT in terms of a step function. So in the step function, VRT will be UT minus 2. So we have these equations, yeah? And in terms of Laplace transform, it will become 1 over S minus 1 over S exponential of negative 2S. That should be the VRS, yeah? Okay, so by using KVL, we are going to get VRS equals to 10 power of 6 of IS plus 10 power of 6 over S of IS. This is based on the KVL for this particular circuit. Yeah, you can work out that the voltage, the Kirchhoff voltage law for the circuit will be VRS equals to 10 power of 6 of IS plus 10 power of 6 of S divided by 10 power of 6 over S times IS. So VRS is 1 over S minus 1 over S exponential of negative 2S, which has been obtained previously, and that should be the equation. And now we can have the IS is equals to S over 10 power of 6S plus 10 power of 6, 1 over S, 1 minus exponential negative 2S, and this will be the equation of IS. Yeah. So, so we know that the V naught S, which is the voltage drop across the capacitor, will be the impedance multiplied with the current. Yeah. So voltage drop across the capacitor will be the impedance multiplied with the current. So that is why we have the V naught S will be the impedance of 10 power of 6 over S multiplied with the current here. So we have the V naught S to be equal to this. Okay, so to find the V naught T in time domain, you need to do the inverse of Laplace transform, or we need to do the inverse of Laplace transform for this term. So I left this inverse of Laplace transform process for you to solve this on your own. Yeah. Okay. If you get any problem with this process of inverse or Laplace transform, you can always contact me. Yeah. Right. So let's have a look at these examples here. Okay. So examples number 3, we are given a circuit in figure question 2b. Okay. So the circuit consists of VT. Yeah. is the input of DC voltage. VCT is the voltage drop across the capacitor. We have R1, the resistor value, and we have switch of S1. Okay, it's given that capacitor C has zero initial voltage. So we are given that initial voltage for this capacitor is 0. And when t equals to 0, the switch of S1 is closed for a very long time. So it means that initially the circuit is switched off, is open. And when t equals to 0, or when t equals to 0 or bigger than 0, the switch is turned on. Yeah, and the circuit reach the steady state condition. Okay, so we are given that the VT is 20 volt, R1 is 5 ohm, and capacitor C is 0.5 farad. Okay, so I hope that you understand the problems, yeah? So we have this circuit. Initially, the circuit is switched off, yeah, it's open, the switch is open. So when T is 0 and bigger than 0, the switch is closed and the circuit is complete. And the circuit reach a steady state condition in this condition, yeah? In this condition where T bigger than 0. So number 1, you have to sketch the circuit in the S domain. So let's have a look at the solution. So in the S domain, okay, this is the conditions given. VC is 0 negative is 0. So when in the S domain, your circuit will become like this, 20 over S. Yeah, because we are given that VT is 20 volt, R1 is 5 ohm, and C is 0.5 farad. So we're going to have the circuit in the S domain will be 20 over S for the voltage source. Resistor is 5 ohm, and the capacitor is 1 over SC, or simply 2 over S. Okay, so this will be the circuit in the S domain. Number 2 is to find the expression of VCS for t bigger than 0. VCS is the voltage across the capacitor. Okay, so to find the VCS, okay, we need to first find the current. Okay, so the current based on the KVL, we're going to have 20 over S plus 5 of IS plus 2 over S of IS. And we can have that the IS will be 20 over 5S plus 2. Okay, so due to this, we can write that the VCS, which is the voltage across the capacitor, will be the current multiplied with the impedance of the capacitor. So we have 20 over S, 5S plus 2 multiplied with 2 over S, yeah, 2 over S, and it becomes 40 over S multiplied with 5S plus 2. Number 3 is to find the final value of VCT for t bigger than 0 using the final value theorem. Okay, so this is to use a final value theorem to find the final value for the VC in time domain. Okay, so you can refer to the properties of Laplace transform in lecture 14, yeah, on the final value theorem. So this is the equation in which we can find the final value for the VT or V infinite by evaluating the limit of S approaching 0 of S of Vs. Yeah, you can refer to this theorem in the properties of Laplace transform. So we can have that, or previously we have that the VCS is 40, the VCS that we have just now is 40 over S, 5S plus 2. So this VCS will be used here because we want to find what is the final value for the VT. Okay, so to find the final value for VT, we need to use this equation. Yeah, limit of S of Vs. Okay, so when we're substituting the S equals to 0, S can be cancelled out initially. So when we substitute the S equals to 0, we are left with 20 volts. So which means that for this VCS, which is the voltage across the capacitor, the final value for it in time domain is 20 volt. Okay. All right. So number 4 is to find the VCT for t bigger than 0, which is to find the inverse of Laplace transform for this VCS. Okay, so for this, we know that from the third part just now, VCS has been obtained to be 40 over S, 5S plus 2. So our task is to write this VCS in partial fraction form. So we have in this form. So I don't want to proceed with this. Find A and B. You can rate it on your own. So end up, we are going to get VCS is 20 over S minus 100 over 5S plus 2, or we can simplify it to be 20 over S minus 20 over S plus 2 over 5. When we do the inverse of Laplace transform, it becomes 20 of ut minus 20 exponential negative 2 over 5t of ut. Okay, so this is your Vt in time domain. Yeah, in time domain. Yeah, the voltage across the capacitor in time domain. Okay, so the last question is describe the behavior of the capacitor voltage Vct throughout the time t bigger than 0. Okay, so we need to describe the behavior of capacitor voltage Vct, in which we have to understand the Vt here. Yeah, this is a Vct, voltage across the capacitor in time domain. So we can sketch the VCT here. So when we sketch this VCT, we are going to get this circuit, or we're going to have this graph, sorry, yeah? We're going to get this graph. So the graph is the exponential terms, yeah, in which the results or the graph will be approaching a steady state condition when the voltage equals to 20 volt. Yeah, this is obtained from this graph. Yeah, so it can be seen that from the final value theorem that we have just now, we can refer to this. The final value for the voltage Vc in time domain is 20 volt. This is the final value for the voltage. So evidently, it is proof that the value is correct, because when we sketch the graph of VCT here, the graph is look like this, where the voltage value is getting steady, or is having a steady state condition when the value of the voltage is 20 volt. Okay, so this is the behavior of this capacitor voltage. Yeah. Hopefully you are clear about these examples. Yeah. Okay, so let's have a look at this example number 4. We are given these problems, yeah, where we have a 100 volt of voltage source. We have 10 ohm of resistor, we have 3 Henry of inductor, we have 15 ohm of resistor, and we have 2 Henry of inductor. Given that the switch S is closed for a very long time and left open for t bigger than 0, which means that initially, when t less than 0, the circuit is closed. So the circuit is open when t equals to 0. Yeah, the circuit is open when t equals to 0. So based on this condition, you have to determine the initial voltage for 3 Henry and 2 Henry inductors. Okay, so we need to obtain. So in these questions, we are requested to find, sorry, it's not initial voltage, it's supposed to be initial current, yeah? Not initial voltage, because for the inductor, it is supposed to be initial current. Initial voltage is only for capacitor, yeah? So please correct this. This will be initial current for 3 Henry and 2 Henry inductors. Okay, so let's have a look at the solution. So in this question, we are not given the initial current. You have to calculate the initial current for both inductors, yeah? So let's have a look at the solutions. Okay. For case of t less than 0, your circuit will be look like this, because when t less than 0, the circuit is said to be a short circuit. Yeah, and we know that in a steady state condition, the inductor will be a short circuit. Yeah, so we know that in a steady state condition, which is for t less than 0, the inductor will be short circuited. So that's why we are going to have, this is the sketch for a time t less than 0. So we have 100 volt and 10 ohm of resistor. Okay, so from here we can find that the initial voltage of the inductor, yeah, can be obtained by simply finding a ratio between the voltage and the inductor, which will be 100 over 10. So that will be the current, yeah. The current in this circuit will be a constant. Yeah, the current in this circuit will be a constant. That is why this current value, which is 100 over 10, which is 10 ohm, will also be initial current for the inductor of 3 Henry. Remember, 3 Henry is located here. All right. Whereas for the 2 Henry inductor, the initial current is 0. Because why? The current will be short-circuited in this path. Yeah, the current will only pass through this path. It won't pass through this second path. Yeah, because this is a short circuit path. The current will pass through this path. Because there's no current in this particular path, we can say that the current, initial current for the 200 inductor is 0. Okay, so we can then say that initial current for 3 Henry is 10 ampere. Initial current for 2 Henry is 0. Yeah, so hopefully you understand the calculation of this initial current for both 3 Henry and 2 Henry inductors. Yeah, all right. So number 2, you have to find the circuit current IT for t bigger than 0. So you have to find the IT. Yeah. So before you can find the IT, you need to find for the IS, or you need to do a transform for the circuit for t bigger than 0. So for t bigger than 0, the path can be ignored. We have this component consists of 10 ohm, 3 Henry, 15 ohm, and 2 Henry of components. Yeah. So let's have a look at solution for the circuit current calculation. Okay, so for t bigger than 0, that should be the circuit's component. So in the S domain, we can convert, or we can transform it to be 100 over S, 10 ohm, 3S. So this will be 30 volt, which is the current voltage source. You can refer to this equation. Yeah, 30 volt of the initial voltage. You have 15 ohm, and for this 2 Henry inductor, the impedance is 2S. Yeah. Okay, so we can use the Kirchhoff voltage law to find for the IS. Okay, so in KVL, equations can be written to be 100 over S plus this. So you can rewrite it to be look like this, where IS will be 6S plus 20 over S plus 5. So in the partial fraction, it is A over S plus B over S plus 5. So please work on your own to find A and B. It is shown here. So we have finally IS is 4 over S plus 2 over S plus 5. So in the time domain, IT will be 4 of UT plus 2 exponential negative 5t of UT. So this is the IT, the current in the circuit. Yeah, current in the circuit for t bigger than 0. Yeah. And finally is to find for the V0 t, which is the voltage across 15 ohm and 2 Henry component, which is to find the V0 t. Okay, so I'm not going to do a solution for this in full. Yeah, so you know that for the V0S, it is simply IS, which is the current that we have obtained previously, multiply with the impedance, which is total impedance. 15 is for resistor, 2S is for the inductor. So we have the V0S will be equal to this. So I left this for you. Please solve this for me. You have to do the long division, and do the partial fraction, and further on do the inverse of Laplace transform to find for the V0 t. So I left this for you to solve this on your own. So if you face any problem with this inverse of Laplace transform, kindly please contact me. Yeah. Okay, so that's the end of lecture 15 and the end of chapter 4. Yeah, so we have finished chapter 4. Yeah. So in next lecture, we are going to learn new chapters, chapter 5, about filters. Okay, so inshallah, we're going to learn this in lecture 15. This is lecture 16. Okay, I'm going to upload the notes in the e-learning. Yeah, so maybe the notes will be uploaded by this week or next week. Yeah, so but first thing first, you have to understand well on this topic of Laplace transform. Okay. Okay, so I did provide to you tutorial 6, which is on Laplace transform and applications. There are a few questions here in this tutorial. So kindly please try these tutorial questions on your own. Okay, try this on your own. Basically, all of these questions, the properties, the applications, all of them have been discussed in lecture 13 up to lecture 15. Okay, so please try to solve this on your own. So for information, all of these questions are basically questions which are extracted from the test and final exam questions. Yeah. So please try this on your own. So if you face any problem with the solutions, you can just contact me anytime. Yeah. Okay then. Right. With that, I end the lecture 15. Okay. So thank you very much. Hope to see you again in our next discussion on chapter 5. Yeah. Okay. Thank you and bye bye.